right, so we'll go ahead and get started. If you need a couple more minutes on the quiz, that's fine. Just put the quiz in the yellow folder when you're done. So if you guys could open to page 45, and while we're opening to page 45, a couple of logistical things as we head into this first test. So today is our last day of new material. We cover something called differentiability. Next class, a couple of things happen. First of all, what is due? Project number 2 is due. Again, I encourage you to check your answers with your neighbors and with people from the other class or people in the studio. Anybody you work with is fine. Just make sure you give credit at the top of the project. Also, next class is going to be our review for the test. So basically, next class will be the first couple of minutes. We'll just talk very generally about the test. And you can ask general questions about the test. But for the better part of the 70 minutes that we have, I think we're going to have you guys work through as many of the sample test problems as you can. These are on page 51. You don't need to go there at this moment, but anyway, if you just search around in the packet, you will find sample test problems. So you'll work through with your with people at your table, getting as many of these done as possible. You know that there are the YouTube videos up there where I work through each of these one at a time, sound and video. So check those out. If you have time between now and Wednesday, start working through these. This is more than the 70 minutes. You won't be able to do all of these in the 70 minutes that we meet on Wednesday. So do as many as you can, come prepared with questions. But for the most part, I think we'll just have folks working in their groups on these next class during our review. And that's that. And also, we have our first test coming up. It's coming up on Friday. So we'll take the test on Friday. I will hand the test back to you graded on Monday. And then on Wednesday, do you know what I'm going to ask of you? Not corrections. That's a nice thought, though. How you want to be graded this coming Wednesday, not 2 days from now, but a week and 2 days from now, is when you are going to commit to what grading option you're going to select. So just to remind you, on the syllabus, there are a bunch of different options for you. There was the standard, there was test heavy, there was test light, and then there was you can personalize according to the ranges that I've picked here. All right, so you don't need to pick at this moment, but some of you have not turned in a lick of homework, so I'm assuming that you're going, something like the test heavy where the homework doesn't count at all, and that's totally fine. When I hand you back that test, on the first page will be a filled-in snapshot of every grade that you have so far. So it'll tell you you've got 100% on the homework, you've got 92% on the questions of the day. It'll give you each of these averages, okay? And then over here in the big blank space, I will tell you if you continue to do the kind of work that you've been doing this semester, here's what your grade will be at the end of the course. If you've decided that homework is going to count nothing for you, I don't want to just give you a standard grade over here where homework counts as something. But at the moment, my default is that everybody is standard until I hear otherwise. So if you already know like which one you're going to pick, where did it go? Here. If you already know what you're going to pick, then on this coming class, this Wednesday, let me know. I'm going to pass out a sheet of paper. If you already know which one you're headed towards, then you'll just circle the one that you want. And then I will give you that snapshot when I hand the test back, because it's silly for me to give you a standard grade if you're definitely not going towards that route. Either way, you're not making a commitment this Wednesday. You're making it next Wednesday. So you will have a graded first test in front of you when you really finally make that choice. But if you already kind of know where you're headed, you can let me know on Wednesday. Are there any questions on that? Okay. So that is that. Any other questions on calendar stuff? Okay, so that is that, and then we'll come back to the packet. So you guys are on page 45. And on page 45, the topic of the day is differentiability. Okay, that's kind of a lie. The topic of the day is really, if I give you the graph of a function, can you sketch the graph of the derivative? And that's not a new topic. We've been doing that for a little while. In fact, on the quiz, there are a couple of questions where I give you a graph of a function and ask you to sketch the derivative. So really the only thing that we're doing here is more of that. But it turns out that there are some functions where you can't take a derivative at a particular point. And so we're just going to look at what that means. What kind of functions don't have a derivative? Because every function we've played with so far has had a derivative. So that's the basic idea for today. So we'll go to number 1, Josh. Okay, so a couple of different ways where a function will not have a derivative at a point. A function will not be differentiable at a point. So take a look at this point right here. We'll call that a corner for obvious reasons. It's two sort of very, very drastic, two different things happening depending on which side you come from. And so let's talk about why the derivative actually doesn't exist at that point. So suppose that I'm going back to my old school definition of the derivative, where we look at slopes of secant lines and then smush together until we get the tangent line. So suppose that I pick a point out here, and I'll draw this red secant line, and then I'll pick another point. Where should I pick another point? Like really close, right? I don't want to pick one so far away, so I'll pick one maybe right over here, and then connect. And would you guys agree the slope of that green line is probably close to the slope of the tangent line at the blue point? Right? It's close to being the tangent line. It's close enough. So the slope of this is, I don't know, 1.4. Just making something up. Now suppose that we pick another point on the other side, maybe not blue. We'll pick another point on the other side, kind of close. So maybe I'll connect to this point here, and I get that slope. And maybe that's negative 1.3. Now, in order for a limit to exist, and by all rights, the derivative is a limit, we need to get the same thing when we come from both sides, right? When we come towards h equals 0 from the left and towards h equals 0 from the right, we better get the same number, because if you get two different numbers, then the limit does not exist. Yes? Okay. If h is going towards 0 from the left, then what is the limit? What is the value of the slope of the secant lines? I said around 1.4, right? The green line is pretty much the tangent line going from the left. But if we go towards h equals 0 from the right, we pick numbers a little bigger than the bad x value. Now what's the, now it looks like it's negative 1.3. The derivative looks like a rational function. Grab a marker. Okay, so let's step to the side and let's take a look. What do we think? If you are going from the left, if you're on the left-hand side of this curve, what kind of derivatives do you have? What kind of slopes? Positive and getting bigger. Okay, so positive and getting bigger. Iris has drawn that first. And then what kind of slopes here? Negative and getting, are they getting smaller? They're actually still getting bigger. We gotta be really clear. Negative 1.3, negative 1.1, negative 0.8. Okay, so those numbers are getting bigger towards 0, and that was the second thing that Iris drew. And so what do we think about the derivative at that point? Does it exist? No, there's this big old jump that's going on. If I try to graph the derivative function, there's a jump. It's no good. So the derivative does not exist at that point because we have two different values coming out of the secant calculation. Okay, so corners are bad in terms of derivative. At any other point besides that corner, the derivative works perfectly well. So I don't want to say that the whole function is tossed out. Just at that one point, you can't take a derivative. If we look at the next picture, we have a vertical tangent line. And so what would you say is the slope of a vertical line? It's undefined, right? You might argue it's infinity. I would accept that argument. Undefined is good too, right? And so what do you get when you take the derivative? You get something undefined. So the derivative at that point, at this one point, which I'm calling C, does not exist because the slope is undefined. Good? Okay, so we've seen two ways for a function to fail to have a derivative. Could be a corner, could be a vertical tangent line. And then there's another way, and I actually don't like this picture that I've put here, so can we replace it with a different picture? I would prefer something like this. And then right in the middle, we're just going to put a hole. And then I'm going to put the dot someplace up there. Okay, and then I'm just going to label a few random looking numbers here. We'll say that this is 1 and this up here is 3. So there's my function. And I claim that this function is not differentiable at x equals 2. Which is rather unfortunate, because do you think you could sketch a tangent line at x equals 2? Sure. I mean, like the curve, it works perfectly well, right? I feel like the slope of that line should be the value of the derivative. I could draw the tangent line even if the point isn't quite there. I know where the point should be. It's where the open circle is. But it turns out we can't. And here's why we can't. And this is subtle. In order for this limit to have any chance of existing, we need the answer when we plug in h equals 0 to be something very specific. All the interesting limits that we did, what did we get top and bottom when we plugged in? 0 over 0, right? Every time we had a limit that wasn't just boring where you plug it in and you get your answer, we got 0 over 0. Okay, definitely we're going to get a 0 in the bottom because h is approaching 0. So the only way for this to be interesting, the only way for this to have a chance at existing is if we get 0 on the top. So to get 0 on the top means f of x plus h and f of x have to be what? Equal to each other. That's the only way I'm going to get 0 up there. F of x plus h and f of x must be equal. Okay, I'm going to replace the x with 2. I'm going to replace the x with 2. All right, how much is f of 2 according to the funny picture I've drawn here? This is 3, so it's something minus 3. Agree? If I do f of 2 plus h, which means I'm very close to 2, right? Because h is going to be some small number very near 0. If I do f of 2 plus h, but I don't actually do 2 plus 0, if it's like 2 plus 0.1, what will you approach if you're at like 1.9 or 2.1? What's the function value? It's very close to 1, right? If you plug in something near 2 but not equal to 2, then the y value will be something near 1. And so somehow upstairs I have a 1 minus 3. And what should it be if my limit is going to have any chance of working? Yeah, we need it to be 0 over 0, right? And it's not going to be. So even though you can draw a perfectly good tangent line at that point, the derivative just doesn't exist there. So what that means is if a function is not continuous at a point, it's automatically not differentiable. And so I think of this as a little ladder. I've got a limit existing. I've got the function being continuous. And I've got the function being differentiable. And for me, there's a little bit of a hierarchy here. The weakest conditions are at the top. The strongest condition is at the bottom. Is it possible for a function to have a limit existing, but to not be continuous at that point? Yeah, in fact, the picture that we just drew over there, that blue curve, the limit exists. As you approach x equals 2, what y value do we get close to? We approach 1. So the limit exists there. Is the function continuous there? No, because that hole, right? Continuity means it's got to be filled in. So limit existing is the weakest condition. If the function's continuous, that's stronger. That's saying something more. Can a function be continuous but not differentiable? Yes, either of the first two pictures that we looked at. The first function, I can draw it perfectly well without picking up my pencil. The first function is continuous everywhere, but because of that corner, it's not differentiable. The strongest condition there is differentiable. Cassidy, did you still have a question? Right. Yeah, that's right. Topher. No, if it's continuous, it definitely has the limit existing. Yeah. So the picture number 1, so we got to be careful about this word limit. In number 1, does the limit exist as I approach the number, just of the function? Yes. Yes. Is the function continuous at that blue point at the top? Yes. Is the function differentiable there? No. And the reason it's not differentiable is because the derivative is itself a separate limit, which isn't graphed here. I'm not looking at the graph of that limit function over there. I'm just looking at the original. So the derivative is itself a full-fledged limit. And in order for that limit to exist, you better get the same thing from both sides. So that limit doesn't exist, which means this function is not differentiable. The limit exists perfectly well of the function, but it's not differentiable there. Okay, so I'm hoping that you guys have a stronger sense of what's going on than when I was in your shoes, because when I took this class, I didn't, you know, like I think I had this ladder kind of memorized, but I didn't really have a sense of why we needed it to be continuous for the derivative to have any chance. So hopefully you guys are in a better place than I was. So let's go down here to number 3. And in 3, we're asked to sketch the derivative of each of these functions. All right, so in the first part here, part A, this function right here does not get as much attention as some of the other like basic functions. Anybody know the name of this function? It's a step function. It kind of looks like piecewise because it's got different rules. So this function here is called the floor function, or I think it's called the greatest integer function. But here's what it does. So this is a symbol that we're going to give meaning to. You know what the square root symbol means, right? Take the square root of whatever's in the blank. Okay, so there's a meaning associated with that symbol, and it says do something to the number that's in the blank. And here's what you do according to that symbol. You round down. Whatever number gets stuck in there, yeah, lop off everything from every decimal part. So we round everything down. So the floor of 3.7 is 3. So it's not round, it's round down. What's the value of 3.1? Also 3. What's the value of negative 1.2? Round down. Negative 2. Oh, I did not mean those guys. Okay. Negative 2. Round everything down. Okay. And so when you plot this function, you get to plot a lot of points. For example, 3.7 is the x, and 3 is the y, it's the output. And 3.1, comma 3. And when you plot enough points, you start to get a sense of the behavior of this crazy function, and it looks like a staircase. Sean? Yes, the ceiling function is with the brackets only on top. Round everything up. Okay. Just one note, this piece right here is really, it's on the x-axis, but I pushed it down a little bit so we could see it. Otherwise, we wouldn't be able to see it. Okay, so let's think about the derivative. So what do you think is the derivative at this point right here? It's 0, because it is its own tangent line, and the slope of that line is 0. What do you think is the derivative at that point? 0. Okay, good. So then I'm feeling like for all of those points, the derivative is 0. What happens at x equals 1? There's a hole. Because at x equals 1, what do we say about the derivative? It doesn't exist. And at x equals 2, the derivative doesn't exist because the function is not continuous. That's one of our conditions. If it's not continuous, no chance at having a derivative. And so I feel like we're going to get lots of these funny pieces always on the x-axis, but holes at all the integers. Okay, let's take a look at the next part. Looking at the tangent lines we get here, what can you say about the slopes? What kind of numbers? Positive, and what's happening to those slopes? They're increasing. Increasing to what? Infinity. Right, at that origin, we're going to get a vertical tangent line. These slopes get bigger and bigger and bigger forever. So that means they're approaching infinity. So I feel like I should draw in here vertical asymptote right on the y-axis, and then draw in something which is supposed to be positive the whole time, but you know, like what number is the slope of this first one close to? Yeah, maybe like a half or a third or something really small. So I feel like close to 0 is what's happening at the far left. So close to 0, but then approaching infinity. So that right there is part of my graph of f prime. And then how about on the other side? What kind of slopes do we get here? Still positive. Positive, and are the slopes increasing? Slopes are decreasing. Closer to what number? Yeah, it feels like these guys are getting flatter, like closer to 0. So it's got to be really big near the origin. So it seems like, again, we're close to that asymptote. And then getting closer and closer to the 0. So what can we say about the derivative of this function at 0? It's undefined. And some folks like to put like an open circle, but you don't need to. I mean, the vertical asymptote is behaving like open circles everywhere. It says it never gets here, doesn't touch. So no need to put an open circle there. The asymptote takes care of it. Okay, let's take a look at part C. What's it called when there are different rules for a function? Piecewise. That's a piecewise defined function. Okay, y equals x. What does that look like? Straight line, 45 degrees right through the first quadrant, right? So it's a straight line going all the way through, except it doesn't go forever. Where does it stop? X equals 3. So what we're going to do is we're going to get rid of all that stuff. And right there at x equals 3, put a hole. And I'd encourage you to make sure that you plug in 3 into the top function, even though technically we're not allowed to plug it into the top function. What do we get when we plug 3 into the top function? We get 3, right? So I'm just pointing out the hole is at x equals 3 and y equals 3. And that's worth finding if you can't just like sketch it like that. Plot a point or two and connect the dots for straight lines. What kind of a thing is y equals 2x minus 3? That's another line, a little bit steeper. So I feel like we should find, for example, f of 3, like legitimately by plugging into the bottom, and also f of 4. I just need 2 points in order to draw my straight line. What do we get for f of 3 in the bottom rule? It's 3, and the second rule is 5. So 3, 3, and 4, 5. So 4, 5 is here, 3, 3 is here. Now, sometimes on tests and quizzes, folks give me like a big empty circle, and then like it's filled in like a little bit inside the circle. And I'm telling you now, you need to commit. The point is either there or it is not there. What is it? It's there. So like if you need to memorize something, like filled in beats empty circle. I mean, like it's there. So don't give me one of these things. Really fill it in. The point is there, and then connect the dots.
I literally just drew one of those as you said.
Yeah. Okay. So what can we say here? Is this function differentiable? Meaning, does it have a derivative everywhere? Where does it not have a derivative? At x equals 3. And which kind of problem do we have at x equals 3? We have a corner. We have 2 different kinds of tangent lines depending on which side you approach x equals 3 from. So let's go ahead and sketch the derivative. I'll sketch f prime in black here. So if I were to think about the derivative at each of these black points, what would I get for the value of the derivative at all of those points? All of them is 1 because the tangent line is itself. So that means everywhere here we go to 1, and then I'm going to put an open circle right there. And then what's the derivative at all of these points? It's 2, slope of that line. So another open circle and then at 2. So that right there is the graph of f prime.
The second one would be a closed circle.
That's what it feels like. It feels like because x is greater than or equal to 3, the bottom rule should get a filled in circle. Yeah, the derivative does not exist at that point. So, even though it seems logical to fill it in because that's the rule where it's greater than or equal to 3, doesn't get filled in. So it's, it's weird. Like you get this thing, it's not symmetric. Like it feels like it should look the same as it did in the original function, but it doesn't. The graph of the slope and the graph of the derivative? I don't know how to fill the dot in. So which one are you saying we would fill the dot in? Yeah, I mean, I feel like when we say slope, when we say slope, we're talking about calculating that thing, and it's different numbers depending on whether you send h to 0 from the left or from the right. So I feel like that function here, this function does not have a slope at the point, at the corner, because it got two conflicting rules. Okay, we're going to skip over that part right there, and we're going to jump to the next page. So here's a new function. On the one hand, it's x squared. On the other hand, it's 6x minus 9. So I'm expecting it's going to be x squared for a little while, and then we're going to have an open circle, and then 6x minus 9, maybe it's something like here, and then up, so eventually would hit negative 9. So something like that is what I'm expecting. I don't know exactly where the hole is, but I'm expecting something like that. So here's the first question, is can we find points of discontinuity? What's the only value of x which is worth trying to see if it's discontinuous? At x equals 3, because the parabola is continuous everywhere and the line is continuous everywhere. And the only potential problem is where the rules change and we might have a jump. So let's see if we can't figure out whether or not there's a jump. So I'll say f of 3 minus and f of 3 plus. 3 minus meaning plug into the top rule. What do we get on the top one? 9. And when we plug 3 into the bottom one? 9. Okay, fair enough. So is it discontinuous at that point? I got the same x equals 9, which means that that I was not right when I drew this thing. So really, where should I draw my line? It's gotta hit the hole, and so actually it's gonna fill in the hole, right? So maybe it'll be something like that. So where is it discontinuous? Nowhere. Where do you think it's not differentiable? Probably at that point. What kind of problem do we have with the derivative here? It's a corner, right? It's something very curvy and something very straight, and it probably is quite pointy at that rule change. All right, so I'm going to show you how to graph this thing on your calculator. I don't think it's all that important, but I just want you to have seen at least once that your calculator can graph piecewise functions all in one shot. If you miss any of the commands that we're about to do, just check out the video on YouTube. So here's how we type it in. It's kind of funny. We type in the first rule, x squared, in parentheses. It's already strange. Then we're going to put more parentheses, and we're going to type in the inequality. I want it to say x less than 3. So you hit the x, and then all of the different inequality symbols are inside of this yellow word test. So we do second math, which brings up this menu. And down there, we're going to scroll down to the less than and hit enter. And then we'll close the parentheses. It's inside of test. So you do second and math. All right, so let's graph this as it is. So do zoom 6 right now. And I claim that it's just going to graph the left-hand part of the parabola, and it should stop at x equals 3. Okay, it does something kind of funny at x equals 3, but at least it cuts the parabola off, right? Even though it doesn't look exactly like that. So I'll tell you what it's doing is it's drawing the parabola until we get to x equals 3, and then it's drawing this. And you can't see it, but trust me when I say it is drawing the x-axis, but you can't see it because it's already drawn there. And the reason for this is that it's trying to connect the last point and the first point, and it does it with a straight line. That's how it connects points. So we know that there's no real line there, but anyway, that's all right. That's not bad. So that's how we cut off the parabola. Now, if we go back in here and we go to the end, we're now going to add the other function. And that also seems strange, but adding the other function means you're going to add this function to 0 if you're on the right-hand side. And what if you're in the parabola part? what's going to be the value of this second function? What's that? Well, yeah, so this function that we're about to type is going to be the bigger than or equal to 3 part, which means that if you're less than 3, then what will this thing be? It's going to be 0. It's going to it's going to add nothing to the x squared part. So that's how it works. So let's type it in. 6x minus 9. And then we do more parentheses, and then we have to say x greater than or equal to 3. And so once you've got it typed in, you can hit graph, and we should see the parabola, and then probably like a corner as the line juts off. All right, so that's actually kind of hard for me to tell that it's not just a whole parabola. So if we change the y max to 100, say, that I think should get us high enough that we can actually see it's a line to the right. All right, so there's my big parabola, and then a line. Okay, so at least we can see it's not both sides of the parabola, right? So we got the parabola and we got the line. What do you think about the corner?
Small corner. It's like this. It's not like a straight line, but it's just barely kind of there.
Yeah, like I don't see a corner in this picture. I mean, I drew something with a very extreme corner that we could just look at it and see. I can't see it here. I don't see a corner.
It's very close to the tangent line.
Yeah, and if it is close, maybe the tangent lines are not too far from each other at that point. Okay, so here's how we can get the calculator to maybe tell us. So I don't think we've done this before. If you go second calc, second trace, I guess, then inside of this selection, there's another option that we have never discussed. It's number 6, dy dx. Recently, we learned Leibniz's notation for the derivative. That's it. So if you go down or just hit 6, it doesn't look like it, but the calculator is waiting for you to tell it what value of x you're interested in. So if I type in x equals 3, which was the place where the rule changed, it's going to tell me, gives me a number, about 6. Okay, it's hard to tell whether there's a corner. I mean, it's pixels, right? Like every pixel looks like a corner. So here's a nicer picture. Again, you got your parabola to the left and your line to the right, except at this moment, the rules are changing at x equals 9. So this is not the right picture. So if I wanted to, I can move this guy over here and make the rules change at x equals 7, right? And so it's just deciding where the rules change. So what value of x was the one for us? X was 3, right? And that's where the rules change. So we go to 3. All right, first of all, does it look like it's continuous? Yeah, does it look like there's a corner?
Yes. It's like, it kind of looks, yeah. Maybe my eyes just blank.
Yeah, you guys are looking for a corner, and it turns out there isn't one for this. That the parabola blends perfectly into the line, something curvy blending perfectly into something straight. It's chosen just so, and it works in this case. Like usually you'd have a corner, just 2 different rules, but in this case, the slope of the last, if I could say the last tangent line on the parabola, it turns out is 6. And the slope of the first tangent line to the line, well, they're all 6. And so it's weird, curvy blending into straight, but it does, it blends perfectly. And if you imagine driving down a dirt road, which is in the shape of this parabola, and so all the time, this is an overhead, all the time I'm turning a little bit to the left, yes? As I drive down this thing, look at it from above, I'm turning a little bit to the left all the time. But if I decide at x equals 3, which is right around here, if I decide at x equals 3, you know what, I'm just tired of turning left all the time. My arms are getting tired. I'm just going to go straight. Where would I go? I'd go right onto that line. And I wouldn't have any kind of a hitch. I wouldn't run into the side of the road. It would be perfect. Blends right into the line. Okay, so again, it doesn't happen very often. Usually you'd expect a corner when 2 drastically different things hit each other, but it could be that they blend in very nicely. All right, so the last thing here is just some vocabulary. You can say that a function is differentiable at x equals 2. Oh, Evan? You know, it's a good question. So this is getting a tiny bit ahead of ourselves, but we'll answer it real quick. With the calendar here, I will tell you that after our first test, so up to the first test has basically been what is a derivative, how can we interpret it? Let's do a limit definition, but recognize they're really, really awful to do by hand. Right after we come back from the first test, we get what I call the section of the course that is all about the shortcuts for finding derivatives. Turns out there are algebraic rules that we can apply, like the power rule that we mentioned a couple of times, to help us find derivatives without going through the long limit calculation, right? And so that's where we start next time. And so because I've taken this course before, I can tell you what the derivatives are of those two functions very quickly, and you guys will be here too in like a week. So the derivative of x squared, I think some of you know the rule already, is 2x. Derivative of 6x minus 9 is 6. So the derivatives are not the same. This is when x is less than 3, and this is when x is greater than 3. But if you plug x equals 3 into both, what do you get? You get 6. And that's what made it work. So it's not that the derivative of the top function is always the same as the derivative of the bottom function, but at the point, they both have the same value of the derivative. Good? Okay. So only because they both happen to be equal is it okay to say, hey, the derivative actually does exist at x equals 3. Just as well, I could have applied it to the top rule. Good question. Okay, so just some vocabulary type stuff here. You could say the function is differentiable at x equals 2, or you could just say it's differentiable at 2. And the assumption is that we're always giving the x values. And that's what we've been doing for, hey, where's this function increasing, right? You would tell me the x interval where the function's increasing. Oh, where's this function concave down? Oh, it's concave down on this x interval. It's always x's that we're talking about. So you don't even need to specify it's x equals 2. It's just differentiable at 2. You could also say a function is differentiable on an interval. Do you think that's an x or y interval? It's x, same as it's always been. Differentiable on that x interval. You could say a function is differentiable everywhere, or if you're in a rush, just say it's differentiable, and we'll assume you mean everywhere. Good? Okay, we have about 22 minutes left in this differentiability activity. The first one says give an accurate sketch. I would like it to be very, very accurate for this one of the derivative. We'll do that down below. On the next page says give a rough sketch of the derivative. You'll do it down below. And then on the next page, it says draw a function that satisfies all of these conditions. And there is an answer key, but don't look at it until you really feel like you've put your best effort forth. Now, I think that you guys will be able to do all three of those in less than the 22 minutes. So once you are finished, jump to page 51 and start on those sample test problems. I'll come around with questions and work with each other as usual.